Okay, we're going to talk about a special type of system of equations called a homogeneous system of equations. Now, homogeneous systems are characterized by a very simple property. Remember that our augmented matrix is formed by the matrix of coefficients and the vector of constants. If the vector of constants is a zero vector, then the system is called a homogeneous linear system. Right? So here we have an example down here. Here we have our coefficients on the left, our variables multiplied by coefficients, and on the right we have all zeros. Okay? So this is a homogeneous linear system. Okay. Now, here's the important question. If you have a homogeneous system, can you quickly find a solution? He's not asking for all solutions, but can you quickly find a solution to this system without row reducing the matrix? Okay, well, it turns out that there is an easy way to find a solution to this system, and that easy solution is expressed in this theorem here. If you have a homogeneous system of linear equations, the system is consistent, there's always a solution, and one solution is found by setting each variable to 0. Okay, now you know the answer. It's quite easy to see that it does work because on the left-hand side I only have coefficients. If I set x1, x2, x3, x4 equal to 0, I only have 0 terms on the left, which is equal to the 0 on the right. So I have 0, 0, 0, 0, 0 on the left, 0 on the right. So if I have a homogeneous system, I can set all the variables equal to 0. I get a solution. And that's what the proof says down here. Now, since this solution is obvious, we call this solution the trivial solution. So any solution in which all the variables are 0 is called the trivial solution. Now, you can think that a system of equations has the trivial solution if and only if it's homogeneous. Okay, you can think about that. If the whole system is not homogeneous, then the trivial solution will not be a solution. You can think about why that is. Okay. Now, here's another homogeneous system. In this case, I have 1, 2, 3 variables. And when I row reduce, I get this following result. Okay. Now, we know that the system is consistent. And we also see that n minus r is 0. And you can see that each column is a pivot column, so there are no free variables. So in fact, the trivial solution is the only solution. So only the trivial solution in this case. Okay, so the question is, are there homogeneous systems that have solutions other than the trivial system, the solution? And we'll find out that there are. In this case, you can work out that this system of equations row reduces to this system here. Notice here we only have 2 pivot columns, so we have 1 free variable. That means that there's an infinite number of solutions. And the way you get those solutions is to write the dependent variables in terms of the independent variable. Our independent variable is x3. Our dependent variables are x1 and x2. If you solve this first equation, you get x1 equals minus x3. If you solve this second equation, you get x2 equals x3. So that's what's expressed here. Now your solution set is equal to the set of x1, x2, x3 that satisfy these two equations. Now we can parameterize this solution set by simply replacing this x1 with minus x3 and this x2 with x3. So all 3 components of the solution vector are multiples of x3, minus x3, x3, and x3. So I could write this as x3 times minus 1, 1, 1. Okay, so there's a free parameter, and I multiply that by a vector. Okay. Geometrically, these are points in 3 dimensions that lie on a line through the origin. Now, why is this a line? Because any multiple of this fixed vector is in this set. So this vector fixes one direction in 3-dimensional space. I'm not going to draw the axes, but you can imagine that this vector, you could plot this vector in 3-dimensional space. And any multiple of this direction is also going to be a solution. So any multiple of this direction, that gives me a line. An arbitrary multiple of a fixed vector will always give me a line. And no matter how many dimensions, here I have 3 dimensions, if I had 5 dimensions, it would still be a line in 5 dimensions because I have an arbitrary multiple of a vector. Okay. So let's go on to another example. Here's another example where we have 4 variables, and when you row reduce, it turns out that you get 2 dependent and 2 independent variables. So the dependent variables can be expressed in terms of the independent variables, which is exactly what he did here. Okay. He rewrote this first equation to solve for x1 in terms of x2, x3, and x4. That's what this equation is here. You can see that this equation follows from this first line here. On the other hand, he solved x2 in terms of x3 and x4. That gives you this equation here. And we can do the same thing that we did before, is we can parameterize this solution set by replacing x1 with this expression and replacing x2 with this expression, and you end up with this. Now I can write this in a different way, and we'll see how this works out later. I have x3 times 1 vector, which is minus 3, minus 1, 1, and 0, plus x4 times another vector. x4, this is going to be 2, 3, 0, 1. Okay. Okay. This is called a linear combination of vectors. Okay. We have this vector, and we have a linear combination. Now we saw before, if I just have one vector and multiply it by something, then it will give me a line. Now if you have a linear combination, you'll get something else. We'll see what that is later on. All right, now there's a practical comment here, is that notice when you do row operations on an augmented matrix of a homogeneous system, the last column always remains at 0. Okay? When you do this, notice that when you row reduce this, it was always 0. When you row reduce this one, it was always 0. So actually, it's not even important to retain the last column when you're row reducing a homogeneous system. Usually, you just deal with a matrix of coefficients because you know the last column is going to turn out to be zeros. All right, now, the example that we saw suggests the following theorem, that if you have more variables than equations, then you will have infinite solutions. Okay? And that follows from what we've seen before, that if there are more variables than equations, then there must be some free variables. If they're free variables and the solution is consistent, then we know there are infinitely many solutions. Okay? So in summary, for a homogeneous system, you either have only the trivial solution or you have infinitely many solutions. Those are the only 2 possibilities. Okay, that's it. Okay, so let's finish off our discussion of homogeneous systems by talking about the null space of a matrix. So null space is related to the solution of a system of a homogeneous system. Okay, in fact, that's how it's defined. The null space of a matrix is denoted n of a. It's equal to the set of all vectors that are solutions to the homogeneous system. Okay, this LSA0 is this system AX equals 0. Just remember that. Okay. Okay, so let's look at some null spaces. All right, here we talk about the null space of arch type I. Okay, so I'm going to jump to arch type I and see what that looks like. All right, arch type I is this complicated system. And in order to verify that those 2 vectors are solutions, you can just plug in the variables to show that those are actually solutions. Okay. Don't know why this is not working. Okay, there we go. All right, so you can work this out that these 2 are actually in there. Okay. All right, so suppose you want to compute the null space of a matrix. Remember that to compute the null space of a matrix, you need to consider this matrix as a matrix of coefficients. In other words, imagine that you're trying to solve the system AX equals 0. Okay, so if you row reduce this matrix, you're going to end up with this matrix. You can do that on your own. Okay, notice that we have two free variables that we can express the other variables in terms of. And those three variables are x3 and x5. We can solve for the other variables in terms of x3 and x5. And we get this final result. Okay. This is similar to the solution sets that we saw before. So this is the null space of this matrix. Okay. Do the very same thing here. When you row reduce this, you get this result. It turns out that the 0 vector is the only solution, so that's all you get. Okay, and then that's it. Very short section there.